share. The share is this one. Can you see?
Yes.
Okay. So this is we started around here and ended just soon after that.
Yes.
Um, one of the problems when I teach online is I have no measure of um, how much to cover, because the temptation when you teach online is to cover quickly a lot of ground. But that is very bad because uh, it doesn't help the students. Students can only pick up at a certain speed. So when I lectured in class, my handwritten notes take me through 5 pages on a good day, and little below 5 on a day with many questions, and maybe a little more than 5 uh, if we're getting very hyper in class in developing many things. But here I have zero idea. So one of the things that you guys have to police me is not be polite about it. And not be polite about it is point out, maybe raise your hand or something uh, to warn me that I may be going a little too rapidly, and I'll slow
Oh,
down. Yeah, I mean, whatever signal you want, maybe something like this means too rapidly, or maybe something like this means too rapidly. Maybe this is better. Uh, then I'll get a hint right away. The other point I wanted to make is the material we will discuss today, which is this solving the Liouville equation, is way more heavy duty than it meets the eye. So it is very deceiving in terms of how difficult it is. And so I think it is always good if you guys write down everything that's on the screen as you feel the importance to do it, in particular anything mathematical. Because as I said, keep in mind that the material is very, you're literally climbing a Mount Everest here.
okay.
And although it may not seem so because things look very benign, but it is a Mount Everest of a climb. So our goal is to. Achha, can you see my arrow if I move this? Can you see this? Okay.
Yes.
So the goal is to solve the Liouville equation, and one way of writing the Liouville equation is for a dynamical variable a is d I dt is square root of minus one I times the operator L times acting on a of t. Now, uh, actually, technically, this is not correct. If I'm really being picky, I should make it just a and not talk about t, because I'm time evolving on the right side and taking a derivative on the left side. So when I'm time evolving on the right side doesn't really have time. The time evolution is done with the Liouville operator. Okay. So the Liouville operator is your operator that takes you forward in time on the right side. On the left side, you are doing the very same mathematics, but with a derivative. That's what the equation actually says. So it is technically incorrect when I write a of t. And most books actually are unclear on this, but it's better to write just a over here. Second point I want to make is that this equation is written in other ways also. Okay. For example, whether you want to use an I here on the right hand side is also a matter of choice. Some people put the I, some people don't put the I. So, but they mean the same thing, excepting that the L operator is defined differently. So you have to be a little careful as to how the Liouville operator is being defined. Uh, I think I pointed out last time, but let me just repeat that the Liouville equation written in this form, where the L operator is not specified, is an extremely general equation of motion. How extremely general? Well, I use the word extremely because it is not only the equation of motion for classical and quantum mechanical systems, it is also structurally the equation of motion for Dirac equation. It's structurally the equation of motion of all equations that go beyond Dirac equation. For example, ones that have made more progress in covering the physics of the spin of the electron, which is not well handled in existing equations. It's also structurally the same as that of Einstein's equation in general relativity. Because in all cases, whatever detailed form of the equation that you get in a given area can be folded into the Liouville equation structure. So that's a point to keep in mind. So if you've ever been asked to deal with an equation of motion, your natural starting point is from the Liouville equation, and then you can, of course, make whatever simplifications, etc., seem doable, and so on and so forth. So this is a very important point to keep in mind, why this equation is so special in physics. Joseph Liouville, who actually developed this equation in the late 1700s or early 1800s, I think, he himself was looking for an equation of motion, and the desire to do an equation of motion essentially was a derivative of studying waves at the time. People started studying harmonic waves, and harmonic waves, of course, lent to thinking of going beyond harmonic. So waves in general alone are very complex, as we know. I mean, there's a vibrant area of research in electromagnetics and acoustics, which are all wave equation based. But of course, when wave equation is in certain conditions and so on, boundary conditions, initial conditions, the solutions can be extremely complex to the point that they're not really solvable. So, and of course, when you get into light waves, you're already getting into special relativity in a big way because light travels at the speed c. And then all those complexities also come in. So there was a real desire, real need, if you will, historically around that time to write down an equation of motion that seemed like the correct thing to do. Now, classically, I have tried to define it a little carefully. I have put ILA as by definition this. This is the Poisson bracket, obviously. Now, since I wrote this particular slide, this is not a slide from in my notes many years ago, I've changed my convention myself. You don't have to do it. Instead of writing H comma A Poisson bracket, I tend to write A comma H Poisson bracket. I mean the same thing, but I write it as A comma H, and I'll tell you why. Well, we are implicitly talking about an n particle system, although we don't have to. We can be talking about a 1 or 2 particle system. So this is just a dressing gown, so to speak. What you have on the right side here, this, by the way, could have been round brackets. So this curly bracket and that curly bracket obviously don't mean different things. They mean different things. This is a Poisson bracket by definition, this, and this is just a normal bracket. So I write A comma H because of the ordering in which I actually write it. So del A, del Qi, del H, del Pi, minus del A, I switch the P and Q. Del A, del Pi, del H, del Qi. So just to remind myself that I don't mess up the ordering and invent an unnecessary sign problem, I tend to write nowadays as A comma H. You can write however you wish, as long as you define it and as long as you know what you're doing. There is nothing that is sacred about this part. Okay, if my internet goes off somehow, you also give me a signal. Okay, then I'll pause and make sure that it hasn't flipped over to a 4G. All right, so that's about what I want to say right now about the Poisson bracket and the setting up the equation of motion here. Of course, if you set up the equation of motion correctly, then this right side here, the last term on the right side, where you have minus del H del Q, is what gives you the gradient of the potential, force being the gradient of the potential. So therefore, you're always intuitively looking for the del H del Qi term with a minus sign when you write this out. And that should be the second term because it's minus so and so, right? The first term is usually positive. So that's another way to keep in mind how to write it without a sign mistake. Small things, but keep them in mind. P and Q are obviously momentum and particle position with conjugate variable notation. Quantum mechanically, I tend to define this. Actually, this is also a little misleading the way I wrote. This is an I, but the dot of the I has gone away. So ILA, same as the right side here. ILA is I over H bar. It's an I, square root of minus 1, I over H bar. H comma A, commutator bracket. So here you basically are using quantum mechanical commutators for setting up what we know as the Heisenberg equation of motion, which is an operator equation describing time evolution in quantum mechanics. So just to remind you, there are two ways of studying dynamics in quantum mechanics. One is using the time-dependent Schrödinger equation, where you actually track the evolution of the wave function. And there, what you measure is, of course, the measurable part of the mod square of the wave function with time dependence. The other way is using the Heisenberg equation of motion, where you don't study the wave function, you study the operator. So this is the interaction picture of quantum mechanics. You study the operator, and once you know the operator structure in time, then you can use the operator on a wave function, and you can get whatever information you would want. Either way, in one problem, you have to know the wave function itself. To know the wave function, especially higher energy state, you have to diagonalize. In dynamics, the problem is a little worse. In fact, a lot worse, because diagonalization alone will just give you the wave functions. But now you may have to diagonalize the wave function multiplied with powers of the Hamiltonian. This is how dynamics differs from statics. So wave function multiplied by powers of the Hamiltonian can make your job of directly calculating numbers quite impossible in most cases, which is why doing dynamics is so impenetrably difficult at times. But we'll come to that in a moment. I also want to draw your attention to the last line I have written here, that I am going to implicitly assume now, unless I tell you otherwise, and I will come to a point where I'll tell you otherwise, that first of all, H is Hermitian. What does H Hermitian mean? That means H is equal to H dagger. But in plain English, H Hermitian means that there is no energy gain or loss in the system. Energy is fixed as a function of time. That's what H Hermitian implies. But we will also assume that A is Hermitian. That simplifies our life quite a bit. And there are good reasons for it, because a great many physics problems, not to mention almost all classical problems, basically end up having A and H Hermitian. But quantum problems may not have A Hermitian, but may have H Hermitian, because that makes it physical. I will discuss what happens when A is not Hermitian. And in fact, I'll say a few words about it very soon. So there is no real loss in our generalities if we assume A and H Hamiltonian, A and H Hermitian. However, there is an enormous gain in our life and simplification of our life by making this statement. Okay. By the way, A and H Hermitian has nothing to do with whether A has an imaginary piece or not. Even with an imaginary piece, it can be Hermitian. For example, if A represents Pauli matrices are actually Hermitian. Okay, so it doesn't stop us from studying magnetic systems, for example. Where does it stop us? It stops us a little bit when you study systems which involve annihilation and creation operators, especially second quantized systems. When you do that, the C and the C dagger, or the B and the B dagger, whatever you use, those actually are non-Hermitian. Okay. So because they are non-Hermitian, you have to generalize how you solve the Liouville equation such that that non-Hermitian nature can be accommodated. One comment I want to make is, I've mentioned briefly that this formalism originally was actually put together by Mori, the first name there, in 1965. And I want to share Mori's papers with you, but at a later point because they're impenetrably difficult. Okay, I mean, when I read Mori's paper, although I know more or less what he's doing, I still get a headache because it is just so complicated. But be aware that Mori wrote two papers, back-to-back papers in 1965, where he put together the whole formalism in one go. Mori's formalism is in general set up for non-Hermitian A's, which is one reason why Mori's formalism looks so very daunting at times, because it just takes what is simple and makes it a layer more complicated. We would avoid doing that. And that simplification and some of these things were done by Lee later on. Lee made it more sort of friendly for applications. Mori's was introduced in 1965, but relatively few applications were done to study model systems. And the reason was that people had great difficulty understanding what he had done because they were not used to seeing that kind of formalism developed. So one reason why I'm not presenting you the Mori formalism in its raw form is because of that. I don't want to make a Hermitian in a non-Hermitian and invent the extra luggage when I can travel lighter. Okay, that's the first. The other point is you have heard, and I've also mentioned the name of Zwanzig. What was Zwanzig's role and why is his name not mentioned? Zwanzig's role is very simple. Zwanzig was inspired by studies on Brownian motion that's been going on for 50 plus years at the time, in the 1950s, to attack this problem by what is called projection operator method. What is projection operator method? Projection operator method's basic idea is the implicit assumption that the dynamics of the system described by your Liouville equation has a fast time scale and some slow time scales. Okay, the slow time scale part is where the focus is, and the fast time scale part is projected out into an integral. It becomes an integral differential equation, where the fast time scale part is more Brownian-like. That is projected out. That was Zwanzig's contribution, and that's where Mori started from. So oftentimes it's called Zwanzig-Mori formalism or Mori-Zwanzig formalism, like that. But the structure of the relations, the recurrence relations and so on that Mori developed, that was really done largely by him with Zwanzig's work forming the base of it. So three people played big role, Zwanzig, Mori, actually four people, and Lee. And in the middle, in 1967, 2 years after Mori's work, a Frenchman spent some time with Mori, and he wrote a very, very nice paper, also in Japanese Journal of Physics. His name was Dupuis, Dupuis, M. Dupuis, Marc Dupuis. And Marc Dupuis was the person who took Mori's formalism and literally managed to strip it down for normal people. So much of the progress using Mori's formalism transpired after Dupuis' paper came out in 1967. So these three papers I'm going to share with you such that you have some idea of what it is like. Okay. Now the ironic thing here is we are talking about all these big words, projection operator, fast time scale, slow time scale. But the actual problem that we have, which is the problem of solving the Liouville equation, it's a bloody first order equation. I mean, how simple can it be, right? But the problem is that the solution to the first order equation incorporates the Liouville operator. And so when you solve it formally, this is the solution. I mean, you can't make it much simpler than this, can you? E to the I LT acting on A at some time t equal to 0 that you set up. And then if you really want to strip it down a little more, where you are writing the L and the A together, where there's the Poisson bracket or the commutator bracket, you can write this, you can write e to the iht, A at t equal to 0, e to the minus iht. These two mean the same thing. These two mean exactly the same thing. There are two different ways of writing the Liouville operator. One is using the Liouville operator, and one is using the Hamiltonian. So in principle, right? In principle, the Liouville equation is trivially solvable. So what is the difficulty? The difficulty is in computing the right side of this thing. This is where all the difficulty is sitting in one dark room, which is very difficult to penetrate into, because this thing is just a mess. Now, let me tell you what kind of a mess it is. So if you actually look into this, this is from some AI generated thing that I picked up, which made my life much easier. But if you actually take this e to the iht over h bar, here h bar has been turned on as something not just one. I have implicitly put the h bar equal to 1 here, which is what I do everywhere. So this h bar becomes 1 in almost all my calculations, and in other people's too. But there is actually an h bar here. So this is being written out. This is the operator at time t equal to 0, and this is the time evolution of it. And this is the two sets of exponential operators that are occurring, that are acting on OS. So if you actually do this calculation, it's not difficult to do. I mean, just to make sure that I have redone it very quickly for this class, I spent about half an hour, 40 minutes yesterday to work it out by hand. And essentially you get what you get below, right? What you get once you collect the terms. So you expand out the e to the iht over h bar, you expand out the e to the minus iht over h bar, you multiply O sub s with e to the minus iht over h bar. You first set that up. So then you have an infinite series here. Of course, commutations are not free. They come at a cost. And then you have another infinite series on the other side of these two. And then you punch them together, you multiply them, operator multiplication. And if you do that, then you get the following structure. You get a time expansion. This is specifically referred to as the short time expansion. Now, as you can see, all orders of time come in here, as they should. The difficulty comes from the fact that while it is extremely simple most times to calculate the first commutator, it already becomes a nightmare to calculate the second commutator, which has three terms, three sets of operators. And as you go deeper and deeper into nested operators, you are getting into pretty cutting edge algebra on the computer. So by the time you get to about 10, 15 orders, you're probably pushing the limits of some of the better computers that you may have access to anywhere. By the time you get to 20 or 30, most computers would not be able to give you anything meaningful. I mean, I had a student in 1996-7 period. He was a very, very bright young fellow. His parents had gone through a divorce, so he ended up suffering a lot for that. And he wanted to get a PhD, but he couldn't pass the qualifying exams. And so this guy, he ended up being advised by me because I was the young assistant professor on the block. And my next door neighbor, who was the director of graduate studies, said, why don't you work with him? He doesn't have a student yet, so just go try him out. So this guy walked in and I asked him what you like to do. He said, I love to do computation. And I said, all right, fine, let's do something. He wanted a master's thesis. So I gave him a problem like this and I told him how to do it. And this concerned a quantum mechanical spin system. and his name was Tom, and Tom worked it out to my satisfaction very quickly. But then I asked Tom to push some of these nested expansions that were coming in, not exactly this, but something similar, as much as possible. Tom went up to about 23 or 24 powers in T, so T to the 24, which is like 12 terms. And the final, he didn't do a time expansion, but equivalent time expansion would be that. And that final step was taking him at the time in 1997, I believe, well over a month to do. Okay, so that's how bad it gets. Of course, computers have come a long way in the last so many years, but yeah, I mean, that paper is still alive. It's an important paper in many ways. So this is the reason why solving this problem is so impossibly difficult. Okay, there is no question really about it. Now, so how do you solve this problem? Time expansion is clearly not the right route because sooner or later, no matter how nice of a computer you have, it is evident that you are going to run out of steam. By the way, one comment is when you study a system like a many particle system on the computer, and when you integrate the equation of motion in time, you're actually integrating for every delta t how the system has changed, right? And then you take stock of how the system is at that instant, and then you add the next delta t and see how the system has changed. If you have a many particle system, you move all the particles around just as the forces would dictate. And from that, you calculate the dynamical variables of interest, typically everything, because you can calculate it. You find out every particle's velocity, every particle's momentum. You find out every particle's acceleration. You want to make sure that the velocity and the acceleration accuracies are to same order. These are done by what are known as predictor corrector codes. So predictor corrector codes will give you these. And the standard predictor corrector codes, one is called velocity Verlet. Verlet is after a name of Louis Verlet, V-E-R-L-E-T, velocity Verlet. Velocity Verlet because velocity Verlet is the version of the Verlet that returns the position and the momenta with same accuracy. Normally, position accuracy would be higher and momenta would be a little lower. But velocity Verlet corrects that. And there is a very good algorithm which is more weighty. The accuracy is higher. It's called a Gear algorithm, G-E-A-R, Gear. Charles Gear was the one who devised it. Charles Gear is a very famous computer scientist. So Charles Gear's algorithm, Gear algorithm, is also a very good predictor corrector algorithm for many body simulations. So those are done using Gear algorithm or velocity Verlet. The reason why I brought up that point is because in some sense, you are doing a short time expansion, but many times over. Every time you do a delta t, you are doing a short time expansion. But the short time expansion is not a short time expansion there. There, the short time expansion is a very, very accurate, approximate algorithm that allows you to go to the next time step with a really high level of accuracy. And that is the reason why you use the velocity Verlet algorithm or the Gear algorithm, because these two algorithms have mastered how to retain the accuracy and take you forward in time. So simulations do take you forward in time. They do it on the basis of a short time expansion, usually to 5 to 7 orders maximum for every delta t. But the series is not a Taylor series. It is a modified Taylor series, such that it allows you to advance in time better than a Taylor series expansion would. And that's where the Verlet's contribution and Gear's contribution came in. Anyway, so let's move away from there for now. Let's move away from there. We know that computationally you can do the short time expansion, you can do a better expansion, but you cannot do computational simulation for every problem. It is not possible. Furthermore, you may not want to do that either, because you may want to acquire a deeper theoretical understanding of the problem. And a deeper theoretical understanding of a problem may not come from a simulation-oriented study. Simulations are very good for giving you broad data on a system and making you develop, allowing you to develop, if you wish, a much more phenomenological way to attack the problem, because you know the answer. So if you know the answer, you can make a model, a phenomenological model of the problem, and solve that model, which may be more amenable to a solution. And then by saying that I know this is the expected result, this is the result I'm getting from my model, I don't have to do the main problem. And that's how you say the simulation and the phenomenology both develop. But if you actually want to do first principles theory, then the simulation is only going to take you so far. It will not allow you to do a first principles theory. So this technique or this kind of an approach is to help you develop a first principles theory. That's the main point. That's the reason why we do this. For example, you want to measure, let's say, a transport problem of electrons or holes through a dirty superconductor or some kind of dirty metal, whatever. Well, you can do it experimentally. If you want to do it theoretically, almost no theoretical method will allow you to do that, because almost all of them implicitly use some kind of translation invariance or some kind of long wavelength approximation, such that short length scale problems can be mushed out, can be, ironed out, smoothened out. Those are the toolkits we use. But such toolkits will not work for making a study of a dirty system, let's say. However, this toolkit will work just fine, because this toolkit has everything in it. Okay? More than what you need, it will tell you. You can do it. So there are great advantages of this method. That said, if you are a theoretician, you want to have as many methods in your cupboard as you can. You have no idea what's going to work where. So the old days of knowing one method very, very well are long gone. We all have to be ready to use whatever method is needed to solve whatever is the problem that we need to solve. And this is therefore one of those methods on your shelf, so to speak, that has its own value. So the continued fraction solution now will solve by starting with this kind of a statement. A of t, which is our solution to the Liouville equation by definition, is some kind of a nu. Nu is an integer here. Nu goes from 0 to d minus 1. A nu of t. So all the time is in A nu of t times F nu. So let's look at it a little more carefully. Clearly, we are thinking in general of A as an operator or a vector, whatever you want to call it. A is an operator. So if A is an operator, then the right-hand side, you need an operator too. And that operator in this case is F nu. A nu t is not an operator. A nu t is a coefficient of that operator. And obviously, here, as you can see, it is a time-dependent coefficient of that operator. So suppose A of t is one vector like this. Then the right-hand side, you can think of as this vector being made up of a whole bunch of F nus. So F0 like an x-axis, F1 like a y-axis, F2 like a z-axis. Then we run out of steam because we can't go to a fourth dimension intuitively. But you can now construct a d-dimensional space. Right? That's why nu goes from 0 to d minus 1. the d-dimensional space, and in this d-dimensional space, you have these vectors f0, f1, f2, f3, f4, f5, up until f of d minus 1. Because you start at 0 and you finish at d minus 1, it's d-dimensional. And a nu of t's are the time-dependent coefficients. So if a is going to dance around whatever way, anchored to some origin, let's say, then a nu of t's will describe the time-dependent coefficients that will allow that dance. And f's are your unit vectors, if you will. Actually, they are not unit vectors. That's why I didn't use the word unit vectors. They are basis vectors along an axis. All right. Now the problem is that if you want to use this concept properly, you have to make sure that all your f's are orthogonal to each other, all of them. So f0 and f1 must be orthogonal, f1 and f2 must be orthogonal, f0 and f2 must be orthogonal, and same goes for f3 and so on. All of these orthogonalities have to come. Now, the big question now that faces us is how do you define orthogonality? What is orthogonality? It is not your XYZ axis that we are talking about in this particular problem. I just gave it as an example. But f0, f1, f2, f3 are just plain old basis vectors in this d-dimensional space. And we are interested in making the f's mutually orthogonal. So we have to define what we mean by orthogonality in this space. And this turns out to be one of the big problems that Mori conquered. How to define orthogonality? So the answer here is a little bit complicated. The complicated answer is there is no single preferred formula for orthogonality. Okay? There isn't any such thing. It's not like, it's not like you have a fever and you take an ibuprofen. No. In this case, you can take an ibuprofen, you can take a Tylenol, you can take some other linear combination of ibuprofen and Tylenol, some other independent, everything is possible. You choose. So this is kind of like that. Now, Mori did something very smart. Mori chose what is called this Kubo scalar product. Now, what is this Kubo scalar product? Ryogo Kubo was one of those incredibly important figures who carved out statistical mechanics, the foundations of non-equilibrium statistical mechanics as we know it today, pretty much single-handedly before Zwanzig and anybody else. And Ryogo Kubo, he wrote a series of papers in the 1950s when he was relatively young to put these together. So Kubo's name actually is tied to the construction of linear response theory that we discussed last Thursday. Kubo was one of the architects of formalizing linear response theory. Kubo was also one of the architects of what we call the fluctuation dissipation theorem. That will also enter here. One of the actors in this drama is the fluctuation dissipation theorem. I haven't told you much yet. I don't need to tell you for a while about the fluctuation dissipation theorem. However, Kubo also brought in a lot of mathematical elegance into statistical mechanics at the time. And like any decent physicist, Kubo was very interested in making sure that whatever we theoreticians do can be connected to what is seen by the experimentalists. Kubo was very dedicated to that cause. And the Kubo scalar product comes from that desire. Suppose you have two of these vectors like f nu and so on. They can be spin operators, they can be momentum operators, they can be whatever variables in classical problem. Let's call them x and y. They're the two vectors. And Kubo described an inner product or scalar product of x comma y, round brackets, as the following rather daunting formula. So integral 0 to beta over all temperature, beta is 1 over kT. Lambda is a dummy variable for beta here, this lambda. So integral 0 to beta d lambda. And because it is being designed as dimensionless, 1 over beta, so the beta in the first integral cancels out dimensionally. So 1 over beta, integral 0 to beta d lambda. That's what that part of it means. The next part of it involves a canonical ensemble average, so TVN ensemble. And it involves x of lambda. Now, this is a very, very important quantity, and I'll tell you in a moment what it is, times y dagger. Now, since y and y dagger are the same for our purposes because we have taken Hermitian Hamiltonian, we don't really worry about it so much, but there is a y dagger here. And then minus x y dagger individually ensemble averaged over. Canonical ensemble average only. X of lambda, in analogy to A of t, is like a lambda evolution instead of an I t over h bar evolution of x. So you remember the formal solution of the Liouville equation? Formal solution is e to the I t Hamiltonian over h bar A times e to the minus I t Hamiltonian over h bar, and then we write it out. So this guy is exactly the same, excepting I t over h bar. Forget about h bar is set to 1. I t is being replaced by lambda. And what is lambda? You see, this lambda is a dummy variable for temperature, 1 over kT. So you can almost think about x lambda instead of a time evolution of x as an imaginary temperature evolution or something like that. It's IT. So IT is becoming temperature. It's like a temperature evolution of x. Formally, that's what it boils down to. Kubo came up with this formula, and this formula actually defines susceptibility. Susceptibility, compressibility, this kind of quantities can be formally defined via the Kubo formula like this. So clearly, Kubo scalar product is not easy to compute because to solve the Kubo scalar product problem, you need temperature evolution information. What is also beautiful is that imaginary time, IT, that's what I mean by imaginary time, IT can be mapped to temperature, 1 over kT. This is in the structure of the Liouville equation, actually, it turns out. So, in fact, this is the foundation of how one does finite temperature studies in quantum using quantum field theoretical tools. This is the foundation. IT is beta, or IT is mapped to beta. So x of lambda then is e to the lambda h, x e to the minus lambda h. And the ensemble average is the same old, same old. If you have an operated theta, the ensemble average in the canonical ensemble in quantum mechanical terms is a trace of the operated theta times e to the minus beta h, this product on the numerator, and the partition function, which is just trace of e to the minus beta h in the denominator. There is a lot going on already. And so I want to draw your attention to all these moving pieces that have now entered our problem because of Kubo. The first thing is Kubo has introduced the scalar product by taking advantage of the canonical ensemble. The canonical ensemble is only meaningful when the system is in equilibrium. So Kubo is basically defining orthogonality with the equilibrium existence being there in mind. But we are doing a non-equilibrium problem. So what does it mean? What it means is linear response theory. Remember, in linear response theory, I took this little cap and I said, if you tap on it, nothing happens to the cap, the energy just disperses throughout the cap. Now, so the equilibrium is there, right? System goes back to equilibrium at the end of the day. So Kubo's point was, I'll have to take advantage of that because then I can say that I remove the system ever so slightly from this equilibrium state. This little bit of energy I gave to the system, this energy now dispersed throughout the system, and the system has returned to the original equilibrium state, not to a new equilibrium state, because this energy is basically infinitesimally small. So to first order, leading order, system goes back to the original equilibrium state. Very important. It's not to a new equilibrium state. It's not like you have a mountain slope. You have an avalanche and the slope readjusts, the new equilibrium state. No. Here, you go back to the original equilibrium state. Very important. So this is what Kubo introduced to the definition of susceptibility in this form. And this is what Mori brought in by implicitly assuming that he could use Kubo's susceptibility formula to orthogonalize the Fs. Okay. How do you orthogonalize something? There is only one very easy method, and that is the Gram-Schmidt orthogonalization method. So I wrote a paper, which I was astonished to realize now 20 years have elapsed since I wrote this paper, which reflects poorly on my age, or my youth rather. This paper, which was written in 2006, was maybe it's called Solving the Liouville. My internet is crapping out again. Hang on. One sec. Let me check. You can hear me, right?
Yes.
Okay. So no bad thing happened then. Gave me a little signal. So so the so I wrote this review at the time for my PhD students at the time who were working on some of these problems, and I wanted them to have everything I tell them more or less easily accessible. So that was the purpose of it. I'll send you guys a copy of this paper in PDF. But in this paper, I wrote exactly what I show here of how to apply the Gram-Schmidt method to do it. So let me just read it up. Constructing orthogonal vectors is a routine problem in math physics. Orthogonal vectors are usually constructed via the Gram-Schmidt process. That can be stated as follows. I think this is the Gram-Schmidt original paper. Suppose one has a complete set of vectors denoted by is G's, collection of G's. Then a complete set of orthogonal vectors is a collection of H's. And the Gram-Schmidt formula says that Hn, any one of these, is Gn, the corresponding G minus, is Gn H1, 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 Gn H2, 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 like that. The formula. Derivation is pretty straightforward, but it's in most math physics books. Thus, the scalar product of two vectors in any problem must be defined to generate an orthogonal set of vectors. But how does one choose a scalar product? And that's the problem that we were just addressing right now. One would typically wish to choose scalar products that render the construction of an orthogonal set as easy as possible. That's the strategy. Your choice of orthogonalization formula should be such that it should be easy to construct these guys. It shouldn't be complicated. Because, again, more baggage means more work, more chance of error, everything. Thus, the choice of a scalar product is an important step and directly affects one's ability to solve a problem. Because if it is too difficult to get the Fs, sooner or later you won't be able to calculate them anymore. It's just too much, right? And the fact is that we usually cannot calculate too many Fs. We can only calculate some. So we are going to, for now, at least we are going to prepare to think for now in terms of Kubo scalar product. I just want to add a few more comments because it's important I do. You can ask me the question. In fact, I often used to wonder, what other choices of scalar product can one think of? And I looked at the papers and I found that everybody uses Kubo, but there were some papers that use something quite weird. People have tried to use the commutator or the anti-commutator bracket itself ensemble averaged the scalar product. That's one thing that people have done. People have tried to use definition of Green's function as a scalar product. So there are many other strategies people have tried to use. Not all these strategies have worked out very well, but Kubo's scalar product generally tends to work in most places. It will not work unequivocally for the non-Hermitian A case. For that, you can use something like a Green's function or an anti-commutator formula. And I'll come to that later. I'll do a separate version of this proof for that case later, because I think it is important to understand that case. One thing I want to show, and this hopefully will give you some good intuition. What does the susceptibility formula really tell us? If you consider a problem where temperature is relatively high, that means it's not zero temperature. Higher energy states matter. If you consider a problem like that, which we will stylistically write as beta goes to zero and T goes to infinity. Basically, it means at finite temperature. Then this equation that you have for Kubo, and basically what happens is that this integral doesn't play a role anymore. You essentially have a high temperature case. And in that case, the scalar product of x and y goes over to what we call the fluctuation formula. The plain old fluctuation formula from statistics. So it is possible that you don't have to do the Kubo product for a given problem, especially if the problem is at finite temperature. You can directly simplify the fluctuation formula as your criterion for orthogonalizing. That is also possible. You'll obviously lose some of your richness if you make the scalar product too simple. And that's what might happen a little bit in this case, but may not be all that much. Vivek, you have a question? No, okay. No, because
Not
so okay.
yet.
Okay. So here, the next thing to make sure that we are clear on is the choice of the initial condition. The choice of the initial condition is very special when you solve these problems. Why? Because the initial condition is when the perturbation happens. That is what linear response theory is all about. Initial condition is when you perturb the system. So F0 by choice, the first basis vector, which is a free parameter. When you choose your x, y, and z axes, your x-axis is what you fix first. Nobody can tell you whether you want to point the x direction like this or that or that. There is no such thing. You can make your x direction whatever you wish. One can say that your y will be perpendicular to x and your z would be perpendicular to x and y. That's fine. But I have no business telling you how to draw an x-axis. Likewise, F0 choice is arbitrary. You make whatever choice suits you. And the F0 choice you make is the dynamical variable at time t equal to 0. So that is the perturbed system at time t equal to 0, you see. And that perturbed system will slowly relax to equilibrium at late times, original equilibrium, before perturbation. So here you see F0 as A at t equal to 0 is what we define as A. Let me now take you back as I was telling you a thing or two about this equation not being written correctly. It should be just A. Just A means A at t equal to 0. That's what it typically means. So I should state t equal to 0 here. When you write down, write t equal to 0. Now, if A is at t equal to 0 and it's F0, then A0 must be equal to 1. Because you see, if you look at the original statement here, if you look at AT, nu equal to 0 to d minus 1, A nu of t, F nu. So if F0 is A at t equal to 0, then A of 0 at t equal to 0 must be 1. And all the other F's must be 0. Otherwise, initial condition on the left and right don't match up. So our choice of F0 being A at t equal to 0, in other words, our choice of linking with linear response theory automatically tells us a little bit about what the A's are. A0 at t equal to 0 is 1. A nu at t equal to 0 is 0. And all the other F's have not come in yet. Only F0 exists. So question now becomes, how do we fix the other F's using linear response theory, using Kubo's scaling product? Now, before we go there, we already know that we have to learn to orthogonalize. And we are going to only orthogonalize using the Kubo scalar product as our tool. So there are two lemmas here, which are very important because about the Kubo scalar product. First is that the order of x and y don't matter. X, y is same as yx. It's a scalar product, so the order doesn't matter. But lemma 2 is that if the Liouville operator enters to act into one of these operators, then the order does matter. In fact, Lx, comma y is minus of x, comma Ly. So if you move a Liouville operator from left to right over the comma, it'll cost you a sign. That's what it says. So let's look at the proof of the first one. So the Kubo product can be quickly stated out like we have before. So the right side here is 1 over beta integral 0 to beta d lambda. And then you have this temperature evolution piece, y dagger, minus. This piece is not important because this piece doesn't have anything to contribute. We might as well forget about it. I've just left it here for now, but it's unimportant. So next, what I do is I just write it out explicitly by removing the angular brackets, and I write down the ensemble average with the trace and so on. Trace of e to the minus beta h, that's by definition what this means, the angular brackets. Then you have the temperature evolution piece, y dagger piece, and then you have a trace of e to the minus beta h. And then you do a little shifting of the variable from lambda, you make it minus lambda plus beta, just a linear shift. Just map it, lambda to minus lambda plus beta. If you do that, then what happens is that this lambda becomes a little bit different. This lambda h becomes minus lambda h plus beta h. And then e to the minus beta h here and e to the plus beta h here, they will cancel out. There's no problem here. And same on the right side also, e to the minus lambda h now becomes e to the plus lambda h minus beta h. Y dagger. I have not written this piece here. It doesn't matter. Or I have written here, but it doesn't matter. So anyway, if you now observe it, this has already become e to the minus lambda h x e to the lambda h minus beta h y dagger. Then what you have is what have I done? I have moved this piece, this block of two operators from extreme right to extreme left by using the cyclic property of the trace. That's what I have done. Okay. So e to the lambda h minus beta h y dagger has been written as e to the lambda h minus beta h y dagger, excepting it has gone from extreme right to extreme left. So now what happens is e to the minus beta h plus lambda h y dagger, e to the minus lambda h, which is this guy here, times x. So therefore, this is the same as yx as long as the Hermitian part is there. So xy therefore can be written also as yx. There's no problem. And here, as I said, I've used the cyclic property of the trace. So this proof is therefore achievable. xy is equal to yx. Okay. We'll now try to do the second part, this part. This part is also not difficult. It's just a little bit of work. So lemma 2, x comma y is minus comma y later on with an IL. So be careful. There should be I here. So internet connection okay? There's something goofy happened. So ILA is I over H bar HA. So right hand side you go first. So this is the definition of the right hand side and the way it's written. I have not brought in the last two pieces which don't contribute. And what I have done here is I have written out carefully what this LY dagger means. LY dagger means HY dagger minus Y dagger H, the commutator bracket that comes in. Okay, so once I have that, then I split up these two things properly. So d lambda e to the lambda h xh, because this h is transparent through this e to the minus lambda h, the commute, h and h commute. So I can take this h and send it through the e to the minus lambda h on the other side. So xh e to the minus lambda h y dagger. This is the y dagger, same y dagger is here. Okay, same y dagger is here. minus, again, e to the lambda h, x e to the lambda h. Now you see what I have done is I have actually taken this this piece uh, this piece here and send this. Wait a minute, what have I done? I've done e to the lambda h. I've moved this h through here. Hx e to the minus lambda h, and then there is a y dagger. So I've basically taken this h on the extreme right and send it through to the other side. So now it has become an hx. Again, cyclic property of trace. So this h from extreme right has been moved to extreme left, hx. And now what is going on is that the Hamiltonian has come first, and there's an x with a minus. So therefore, you don't want to write it like that. You want to write it as xh minus, you want to write it as hx minus xh, but it is xh minus hx. So therefore, the minus sign comes in. And that is the origin of why that minus sign comes. Okay. So this is not really very difficult. It's just a little bit trickier because you have this additional minus sign that you have to adjust, which is why you have to make sure that you account for it. And again, like in the first case, you are using the cyclic property of the trace to make this proof work out. So now we have shown our two lemmas, and they are okay, they're correct, they are valid, the relationships. And we are now in a position to see if we can use these lemmas, 1 and 2, to actually use the Kubo scalar product to construct the orthogonality among the f's. That's what we want. So let us just play around a little bit. Let y dagger be equal to x, then Lx comma x is equal to minus x comma Lx. If I make y dagger equal to x, then Lx comma x, suppose y dagger, is equal to x comma Lx, minus sign. But from lemma 1, this is like y only. So Lx comma x is also x comma Lx. So if I write y dagger equal to x, then it is imperative that to reconcile with the two consequences, that Lx comma x is equal to minus x comma Lx, and Lx comma x is also equal to plus x comma Lx. To reconcile with these two, the only choice I am left with is Lx comma x is equal to 0, because only if it is 0, then both of these conditions, which are correct, will hold. But Lx is already same as x dot. So x dot comma x scalar product then becomes 0. So therefore, I can make x dot a choice for f1. It's okay, because f1 and f0 would then be orthogonal. It's okay. So I can write f1 is equal to IL f0. That can be my first basis vector after f0. That's all right. No problem with that. Again, just to go over this, what we have really done is we have made y dagger equal to x. If y dagger is equal to x, then we have Lx comma x, and we already know that if we move the L, there is a minus sign that comes. We already know that. And the other is from lemma 1, Lx comma x, this is like x and y, is also equal to y and x. So Lx comma x is like x comma Lx. That's also true. So to satisfy both of these, we have no choice but to say x dot comma x is 0. And that gives me an f1 which is orthogonal to f0. So far, so good. Now bad things will happen. Not bad, but complications will come now. So you see, if I want to make Lx comma Lx, then Lx comma Lx is not 0. That's like the length square of Lx. How can that be 0? But Lx comma x is also equal to minus L squared x comma x, because I can move an L to the other side by paying the price of a minus sign. That was lemma 2. So Lx comma Lx non-zero means minus L squared x comma x is non-zero, which means x double dot comma x is non-zero, which means while x dot comma x is 0, x double dot comma x is dead on arrival. That doesn't work. But x triple dot will work with the same logic as x dot work. So if you want to make an orthogonal set like this, x, then Lx, this is not a dot, Lx, L squared x, only the odd ones will be orthogonal. The even ones won't. That's the problem. It doesn't work. It doesn't work. It doesn't work in general. It works for F0 and F1, but it doesn't work from F1 to F2. So from F1 to F2, you have to now come up with a new strategy. You see, this is how wildly I miscalculated the amount I can teach in a day. My finish line that I had planned for last Thursday, without thinking deeply, was a slide after this slide. That was my finish line. That's how quickly I would go if I were giving a talk. But here we are following everything carefully, so it's impossible to get there. So I've pretty much used up the whole class period. In fact, it is 3:15 now, almost 3:13 for this. So anyway, we now have to figure out how to make F2 orthogonal to F1. That's the first goal we have. So we want F2 comma F0 is 0. We want F2 comma F1 is 1, because below 2 we have F0 and F1. Both of them must be orthogonal to F2, right? And so F2 equal to IL F1 would imply that F2 comma F1 is IL F1 comma F1. And that's all right. So I can make that to 0. F2 comma F1 is IL F1 comma F1, and that can be 0. But F2 F0 will not be 0. So there is a problem. Because remember, F0 and LF0 was 0 before. So F1 comma LF1 should be 0 also. So that's fine. But this guy, F2 F0 orthogonality, doesn't work because I can move one of these L's to the other one, and then it becomes a length square of LF0. And a length square cannot be 0. So we have a problem here. So what to do? Well, what we do is we now introduce some unknown here. So we say F2 is IL F1 plus some X1, whatever the X1 is. And we'll try to see if we can actually argue out what this X1 must be. So IL F1 comma F0 plus X1 comma F0 is equal to same as IL square F0, because this is F1. So F1 to F0 we are going down. So IL therefore gets squared. IL squared F0 comma F0 is equal to minus X1 F0, because we want this to be orthogonal. F2 and F0 to be orthogonal. But IL F1 comma F1 is already equal to 0. IL F1 F1 is already equal to 0. And IL F1 comma F1 will come because I also want to make sure that F2 and F1 are 0. So there are two. Okay, let me be clear. I'm not sure. Maybe I'm confusing everyone. By 1 and 2, I have 1 and 2 marked here. So where did I write that? To 0. And 2 is F2, F1 is equal to 0. So we want to insist that F2, F0 equal to 0 and F2, F1 equal to 0, 1 and 2 are both satisfied, for which we have assumed this form now. So we can find the X1 that will allow me to work with that. So 1 implies IL F1 comma F0 because 1 was F2, F0. F2 is IL F1, right? F2 is IL F1 already. So IL F1 F0 plus X1 F0 because I don't know what this F2 needs to be to work properly. So IL F1 comma F0, X1 F0, and that means that IL whole square F0 F0 is equal to minus X F0. That's what 1 implies. This is F2 F1 equal to 0. This is number 2. So IL F1 comma F1, this is F2 F1 plus X1 F1 is equal to 0. But IL F1 comma F1 is already 0. That orthogonality we have already shown because F1 and F0 are orthogonal. So if this is equal to 0, that means the inner product of X1 and IL F0 has to be equal to 0 for these two to be satisfied. At this point, the question now becomes, what is this structure of X1? So X1 can have two possibilities. X1 can be simply C times A, and X1 can be some C prime IL whole square times A. These are the only two choices for X1. That's what these two orthogonalities imply. If you work it out slowly, you will see that F2 F0 equal to 0 and F2 F1 equal to 0 imply there are strict conditions on X1. And that strict condition is that X1 must be some constant times A, or X1 must be some other constant times IL square on A. Both work. So what to do? If you assume IL square F0 F0 equal to minus X1 F0, if you assume that, here, that's from condition 1, F2 F0 equal to 0. If you take this, if you assume that, then since F0 is by definition A, you are saying that A double dot, which is what this is, A double dot comma A is minus X1 A. But X1, first choice is CA. So that means C must be equal to A dot inner product over AA, inner, which we can call capital delta 1. So then C must have this structure, and if C has this structure, then F2 is IL F1 plus delta 1 F0. Here we have arrived at one recurrence relation that would work. Without imposing any severe restrictions on the vector space in this case. So this works, but this doesn't impose any restrictions on the vector space. This satisfies both choice 1, choice 2, everything. Sorry, both equation 1, equation 2, everything. Equation 1, equation 2, again, remind you, is F2, F0 equal to 0 and F2, F1 equal to 0. All right. So whatever choice x1 to C prime, IL whole squared on A. This was the other choice that we were able to establish. So if x1 is C prime IL whole squared times A, then IL whole squared F0 is equal to minus x1 comma F0. I know this is very confusing actually when you start going through it, but if you want me to back up anywhere, just let me know. But essentially, if we make x1 equal to this guy here, then IL whole square times F0 comma F0 must be equal to minus x1 F0. Actually, there should be a C prime here. Anyway, or a C prime on the other side, whatever it is. So then IL whole square F0 is equal to minus C prime IL whole square F0 comma F0. And that requires C prime to be 1, minus 1. And that would allow F2 to work, but it also makes F2 equal to 0. That we were not bargaining for. We wanted a finite F2. We wanted an F1 and an F2 and an F3 and an F4, all of these. We didn't want anybody to be dead a priori. But this choice, the other viable choice we had, that basically ends up killing F2 itself. What does it physically mean? If F2 is 0, that means you have only F0 and F1. That means your dynamical problem can be necessarily solved by two basis vectors. But that is weird, isn't it? You have all these complex dynamical problems and two basis vectors can solve it. Actually, it violates the completeness of the Hilbert space that we are weaving. You see, one of the properties of the Hilbert space is also completeness. And if F2 equal to 0, it is in violation of the completeness of the Hilbert space. So this choice forces dynamics to be in a two-dimensional Hilbert space, F0 and F1. And that is not physically viable. So I'll just take 1 minute to go over this one more time. We had established that to construct, we had established that first F1 is ILF0. Then we found out that the odd derivatives were orthogonal to the previous vector, but the even derivatives were not. To the first vector, but the even derivatives were not. This was what we found here. So then we wanted to find out what is the general structure of F2. And of course, we have to insist F2 is orthogonal to F0 and F2 is orthogonal to F1. So F2, then we can start with a very simple statement. F2 is ILF1, which already guarantees F2, F1 is 0. But it doesn't guarantee that F2, F0 is 0. So clearly F2 can't be ILF1. We already know that. We already know that the second derivative problem is not orthogonal. So F2 cannot be ILF1. We know that. And here we are just saying the same thing. Then what we are saying is that let's make F2 equal to ILF1 plus X1, whatever that X1 is. So ILF1 comma F0, F2 F0, we're trying to do, plus X1 comma F0, then can be written as IL square F0 F0 minus X equal to minus X1 F0. Because this is 0, right? That has to be 0, so minus X1. Similarly, IL F1 comma F1, because this is F2 F1 equal to 0. plus x1 comma f1 is equal to 0. But IL f1 comma f1 is already 0. So for this to be 0, x must have specific properties that it must satisfy. One property is that x is just c times a, and the other property is that a only, but it can also be the double derivative here. That will also work. And then we found out that if it is the double derivative choice we make, then f2 itself becomes 0. And that will violate the completeness that we must have. So the logic here is that we have no choice but to generalize this approach, this recurrence relation, which is Fn equals IL Fn minus 1 plus delta n Fn minus 2. So that's really what we have been trying to show, which propels us to this recurrence relation and this structure of the delta news. So this is correct actually. If you assume that your A is Hermitian, if you assume that your H is Hermitian, then you can get away with what is called a three-term recurrence relation. 1, 2, 3 term. Mori's approach gave you a 4-term recurrence relation. And we will see that later. But this gives you a 3-term recurrence relation, simpler. But it allows you to construct correct orthogonal basis vectors all the way from 0 to infinity. That's what it allows you. Now, let me shed light on something that you may not immediately see. What are we doing? We are constructing a Hilbert space. And in that Hilbert space, we have defined a scalar product to make sure that we can impose orthogonality. That's what we are doing. So this scalar product enters and manifests itself to this capital delta nu, which has the following form. Physically, what is it? Physically, it is the length square of f nu over the length square of f nu minus 1. That is what delta nu is. So delta 7 is the length square of f7 over the length square of f6. Delta 55 is the length square of f55 over the length square of f54. So these deltas basically give you a geometrical ratio of the lengths of these two adjacent vectors. So delta nu, therefore, carries information about what? About the hypersurface of the Hilbert space. The Hilbert space has its own geometry in this abstract d-dimensional space. It has its own geometry. And that geometry is embedded in delta nu. That information is embedded in delta. So delta 1, delta 2, delta 3, delta 4, delta 5, delta 6, all the way, it is allowing you to define the nature of this hypersurface. So therefore, the dynamics of the system, information about the dynamics of the system is therefore getting embedded in the hypersurface. So therefore, you should expect the patterns of delta nu to be of great importance in understanding what kind of system dynamics will emerge. Everything is buried in the patterns of delta nu. And of course, there are some definitional issues. The highest delta is d minus 1 because delta d would be 0. That's how we have defined our space, d-dimensional space. And the highest fd would be 0. And by definition, f starts from 0 only. So f of minus 1 is also equal to 0. And the lowest delta is delta 1. There is no delta 0 because it's a ratio of two consecutive length squares. So we have arrived at how to construct the basis vectors. We still don't know how to get the A nu of T's. So you can imagine that we are constructing a building. We have constructed the scaffolding on how to build the building. That scaffolding is your set of F nus. The building itself will require information about not only the F nus, the scaffolding, but also about the time-dependent coefficients that must be tied to the scaffolding. That's your building. So since the building is a real thing and not the scaffolding, the solution to the Liouville equation will not come from F nu. It will come from A nu of T's. We have just broken down our problem into solving for basis vectors and solving for these time-dependent coefficients. And the basis vectors are relatively straightforward in some sense, not at all in real life. But the time-dependent coefficient is where the real problem is going to come. And that would be a very, very eye-opening thing for you if you haven't encountered it before. Because for the first time, you will see that there is a problem in which you need to know what's happening at infinity to solve the problem. Okay. Dynamical problems have a character. All dynamical problems. What is the character? The character is you can't solve a dynamical problem fully step by step. If you want to do it step by step, you're doing a short time expansion, which we saw. But if you want to actually solve it, you have to solve it for all times completely and simultaneously. And that is the reason why dynamical problems are so interesting and so difficult. Because you have to guess in a way what the solution is. What does this approach do? Modi's approach, Lee's approach, Swanson's approach, they make an effort to get you to the end point by looking at the problem. You still have to solve it, but they take you through a tunnel to get to the end point, such that you have some idea of how to do it, which most other approaches can't do. Okay, I better finish because I am way over time. We will continue on Thursday, and I will focus on how to construct the second relation. This is the first relation, first recurrence relation, or R1, we call it often. Recurrence relation 1. We'll try to solve recurrence relation 2. First construct it and then discuss how to solve it, which turns out to be a life and death problem. So we'll go there. All right. Thank you. Thank you.
Yeah. Thank you.
Okay. Good night.
Yeah. Good night.